recording.
So today we're going to talk about assembly process collaboration at Proplanner, in particular with the concept of the digital twin and the digital thread, which we call the digital T's. I think it's important to start with the fact that when we look at how organizations bring new products to the market, bring new products to the line, really, to production, we have this process that's pretty mature, or it's maturing on the CAD side, the product engineering side. It's when we have an engineering change order that reflects a bill of materials, a CAD model, something that we want to build. From that point, what happens to the data becomes a lot less defined. It's kind of the wild west of manufacturing data. And it's an area where people are spending quite a bit of time. It's the area in our view at Proplanner where the digital twin really takes shape. I mean, certainly you could say that a CAD model of the product, a particular customer order, a configured product, represents a true digital twin of that product. But what's more important, we believe, in PLM is to look at the digital twin, not just from a CAD model, but from a manufacturing process, from work instructions, from documented serial numbers of components that go into a particular customer order. We believe that really reflects the true digital twin. Now, when we talk about the digital thread, what we're talking about is an electronic flow of information from the ECO, the EBOM, the CAD model, through to shop floor execution, where we do not have people typing in data. We do not go to paper. We're not going into Excel spreadsheets and copying and pasting and typing and color coding and printing and getting out your magic markers. The digital thread basically means that when that component's part number is authored as a CAD component in product engineering, that it isn't touched by a human, it's just referenced throughout the rest of its life cycle. That reduces the chance for human error, that enhances the ability to relate to that data, to correlate to the data, to look at its true life cycle, because there actually is a digital connected thread from the life of that component and its data record in computers from beginning to end. And so this old Excel, PowerPoint, Word world, this blue box that we call the how, is really where we spend a lot of our time. It's part of what we call manufacturing or assembly PLM, manufacturing process management, a manufacturing data model. It extends into the shop floor execution world through manufacturing execution systems, through shop floor PFEP systems, Kanban, kitting, and then into monitoring and reporting in Andon. Obviously, in this process, we are communicating with the ERP system, which we're assuming is generating the order requests from sales. It is ordering the materials so that they're accessible to us when we need them. We have to request them, but at least those materials have been paid for, that they've been identified as to their location, and that we may be able to request, 3 of 100 parts that were ordered. We can request the 3 we need right now. That's really our function. ERP's job is to make sure we have the 100 we need for this week or for whatever the order cycle is from purchasing's perspective. But ultimately, when we need parts, we can request them and they're delivered to the right place at the right time. And that's our job on the execution side. And then we just tell ERP what we did so that it can account for the inventory levels, it can account for costing and things like that, which it does very well. But the execution side and the engineering side is really a very tightly related relationship between when the product is authored and when and how it's manufactured. Now, what makes this a little more complicated is that we have multiple configurations, we have multiple assembly lines, multiple configurations of the product, we have multiple assembly lines we build it in, we have multiple cycle times in terms of The processing times that steps take in those lines vary considerably. We have to consider the variability of different model mix scenarios on these multiple lines. And then of course we have lots of different equipment, people, resources that we need to efficiently allocate in a dynamic manner. The day of putting 3 people at a station for next month, regardless of what I'm making or how much I'm making, is over. We need to be able to float that work, that labor, those pieces of equipment to where they're needed at any particular point in time. So we have 3 big bubbles that we like to look at. The BOM, which really starts as a engineered bill of materials. These are the components that product engineering assumes are needed. And then we go into the MBOM. And then, so from the engineering change order and the bill of materials, the EBOM, we go into the manufactured bill of materials, which may include things like consumables, packaging. We're also going to deal with not just the fact that there are 8 bolts, but which bolts are actually assembled at which time. So we're dealing with instances of items at certain times when they're needed, which is also part of the MBOM. And then the MCO workflow, the manufacturing change order, because every one engineering change order could be represented by multiple manufacturing change orders. It could trigger multiple manufacturing change orders, where change orders might relate to logistics problems or changing task locations on assembly lines or tooling changes. In fact, even if we don't change the product, we can have manufacturing change orders that are instigated on the line that because of a process improvement or a tooling exercise. The bill of process, the routings, if you will, is what defines how we make things, where we make things, the labor content required. And then when we get down to the execution level, that really manifests itself in two areas. One in the logistics side, which is often seen in Kanban lots and kitting, where we actually generate a part kit for a specific customer order. And then the various shop floor work instruction, automation tools on the floor that we need to work with the workers, that we need to work with the machines and communicate what's happening eventually to maybe a dashboard, an and-on system. So Proplanner focuses mostly in this area, but we do a lot of work in the MES, as you'll see, and we're doing pulling a lot of material, doing a lot of handshaking with the product design world. So the Proplanner space in the MRP, ERP space, we're obviously not ordering parts directly from vendors, but we are requesting parts. So that green box is can be a little shared, I'll bet, put it between what we do at Proplanner and what your ERP system may do. And that will be different for every plant, probably. Now, when we look at the process plan, which is really the heart of the manufacturing digital twin, it isn't just a bunch of parts, but it's how those parts are actually made into the product. We do have some terminology that's important to standardize. One thing that we have the line station resources, which really relates to the plant and what's in the plant. But in a station, we typically have an operation on the process side, and that operation reflects all the work assigned to each worker. So there may be 3 or 4 operations in a station if there are 3 or 4 workers in that station, but that reflects all their combined work. Now that work represents a bunch of what we'll call high-level assignable tasks. So when I say an assignable task, that means a task that could be put into one operation or another operation. It could be moved to a different operator or to a different station. So it wouldn't be like a grasp or a reach or a walk. That would be a time element. But a task is actually put a bolt on, put on a bracket. We're assuming that those would be things that could be assigned to different people and done in different stations. So that assignable work we call as activities, and below that we refer to the pieces of an activity which are simply not independently assignable. And they really form both work steps and elements. Elements would be more subsets of things that a person does that we can attach time to or ergonomically assess. And work steps would be things that we would describe in a work instruction document and help the operator to perform that task. And work steps and elements may share, may not share. It really depends, once again, on the organization. The collection of operations, of course, which is a population of tasks that go into making something, is manifested in the routing, and routings typically in our world are configurable, which means that we do not create a routing for every end item that's made, but the routing essentially lists all the things that could happen on a line. And that's why there's a relationship between a process routing and an assembly line, because an assembly line has a collection of tools and tasks and people, resources that are used to make a variety of things. And so what we do is we essentially configure or filter that routing for a particular customer order, taking out those things that are not needed for that order and leaving those things that are. But instead of generating a routing for every possible customer order, we're actually just generating a routing for the line, making sure that when we apply an order to a line, that all the things that order needs are capable of the line. When we look at then the process side of that off to the right, we're looking at takt time. We look at, which essentially represents the pace of the line, how often a unit can come off the line on average. That's going to vary a little bit if indeed we have a lot of mixed model production where some products take a lot more time than others. We may have the lines penalized quite a bit in terms of efficiency when we have that kind of variability. We try to keep that out of there. But the reality is the takt time represents that overall pace of the line, the longest cycle time that we incur in producing the products in that routing are going to drive that takt time pretty heavily. Consumption then is something that we're doing. We're consuming parts, we're consuming tasks as we make them. And of course, once again, the takt time and what we consume is heavily driven on what it is we're making. In other words, what is the product model? What are the options that are in that model? All of this, of course, is manifested in the form of a bill of process, which is configurable. In other words, we can have a bill of process, a process routing for everything that we make, or a bill of process, which is just a general definition of the processing capability of this area of the plant, essentially this routing. Now, what makes things a little more difficult is the blue bar at the top. That's the concept of the scenario. And in the case of the scenario, what we're saying is that while we generate this very detailed process routing, this bill of process, that is for a particular approach that we may take to manufacturing. By approach, I may mean based on the production volumes we're running and the variety of products that we're running and the particular versions of products that we're running, the variants, that's going to drive a certain allocation of resources. In other words, a certain number of people available in each station. So the scenario, you may have a 14-person line scenario, a 16-person line scenario, and an 18-person line scenario, which of course will change everything below it in terms of what tasks are assigned to which people on the line, where parts are consumed at, where parts then thus need to be delivered to, and so on. So on the top bar, we have scenarios. Once again, the 14-person line, the 16-person line, 18-person line. In the bottom, we have all the process knowledge to make that happen. And on the right, we can then take customer orders and generate very specific routings, task lists, work instructions for each of those customer orders, for each of those scenarios in each of these bill of process routings. When we look at a workflow of a manufacturing change order, what we're really saying is that we're going to start with this bill of process definition. We're going to identify these tasks in this routing and what parts that they're going to consume, and thus how long those tasks take to put those parts on, and what tools are required to do it, and what stations we want to do it in, and what then work instructions we're going to need to author to describe how that happens. And then we're going to basically need to make sure that the implant logistics system, the plan for every part, is capable of producing, delivering those input materials where needed, when needed. And thus, we need to be able to generate on the floor at the time, start of production, what those instructions are for those operators that need them and what those part kits and part deliveries are to make that happen. That's really where the publishing happens. So this is really the life cycle of an MCO. And as you can see, if I can have an accurate EBOM, which goes into an MBOM and an accurate bill of process routing, I have an electronic model of that entire product and its manufacturing process from design to execution. Okay, that represents a true digital twin of what's being produced and its life cycle, not just what the work instruction was and the part kit was and the serial number of the motor and transmission that were put into it that reflects the data model of that specific customer order, but the whole life cycle ahead of that as to who did those tasks when it was actually made, and when were those tasks approved, and who proved them, and when did they come on the line, and when they go off the line, and that correlation, that relationship between these tasks and these components and their life cycle, all being electronically linked, is the digital thread. The fact that they do not exist in separate documents and were typed in at different times by different people. We can carry this through electronically. Everything is drag, drop, okay? You're correlating, you're referencing, but you're not authoring. Once that part gets authored in the product engineering phase, there is no reason for a human to type that part number in. They should always drag and drop it and relate it to something else, so that there is an electronic thread, a digital thread of the life cycle of that component through its process. Same thing's true for process routing. When I author a task, it has a life. That task is then linked to components. It's mapped to stations. It's mapped to people. Information is authored about how the task is performed in work instructions, but it is not retyped in. It is not externalized in other systems. It may be communicated and shared, but essentially it has its own life cycle, and we can trace it, also part of the digital thread. So part of this process to work in a concurrent engineering environment requires a gating process. What we mean is that we're going to have people designing the product and changing the product. At the same time, we're going to have people authoring the manufacturing process, generating line balancing, publishing work instructions, and delivering parts to the line. All this happens at the same time. The only way that this can happen at the same time is if we have very well-defined publishing gates that allow data to be transmitted to the next phase in a well-defined process. And then when that data is transmitted, the people who transmitted it can go back to creating then the next generation of that data. While the next step in this process, those people now start with the data they received as the beginning of their new generation of data. So we've identified some key gates here. The gate where we receive the product data, the ECO, the engineering change order, and the EBOM. The gate where we link the process, generate the MBOM, and start linking the process, defining the process to make it. The gate 3, where we start relating the process to people and tools and stations, the line balancing phase, the scenario development phase. And then once that's been completed, the gate where we publish this for the world to see, for the workers to see the work instructions, for the logistics people to get the part delivery requests, for the ERP system to understand what's going to be built in the future, AKA the MBOM and the routing, or what was built yesterday, depending upon where we are in that life cycle. So you can see this gate here in this diagram. We're starting with this EBOM coming into this process database world where we have tooling and we have time studies and ergonomics and work instructions and workstations. And we're basically relating these tasks that do things to assemble this product by consuming those components we got from the EBOM and relating them to the stations and the tools that we're authoring in the bill of process. Once we have our completed bill of process, that's where we enter the line balancing gate, gate 3, as we mentioned, where really this is all about assignment. It's about trying to make sure that we know where the tasks are going to be done and that the parts and tools and people are needed and that it's a good, efficient use of resources. That's when we really enter gate 4. That's where we start publishing information, and then gate 5, where we start executing published information. And so you can kind of see how this flows. And each of these gates has a very well-defined process. And this is part of the digital thread. The digital thread can only work if there's a well-defined gating publishing process to allow the data to flow in a meaningful way to support concurrent engineering in the organization. So here I've got these different 5 steps, and we're just going to kind of walk through those at one level of detail below. So step 1, as I mentioned, we're authoring this manufacturing change order. We're authoring this MBOM. We've grabbed the EBOM on the left. We've related it to the last version of that BOM that we saw, the MBOM on the right, and we are synchronizing those changes. What does that mean? Well, they could engineering could have changed quantity of parts, they could remove parts, they could have added parts, they could have changed the parts level in the BOM structure, could have been a replace. This is a human activity. The engineer needs to understand how that EBOM changed and how it affects the new version of the MBOM. Now, the MBOM initially could be just a copy of the EBOM, but over time, once new versions of that BOM come into play from engineering to manufacturing, this information has to be identified. The good news is, once the manufacturing engineer understands how that new version has been modified, what's new, what's different, they can flag those changes so that they can be understood by the rest of the manufacturing change process, or the MCO. And this is where we get into this concept of not only authoring the routing, but consuming the MBOM from the routing. Notice I say not consuming the routing from the MBOM, because the routing is its own process tree structure. Just like the product has a product tree structure, the process, the routing, remember all the tasks that can be performed on a station, on a line, okay, consisting of stations, has a tree structure, a precedent structure of how things have to be done, the order in which tasks can be performed. That is a tree structure. And so we consume the MBOM tree structure into the process routing tree structure. And that's essentially what's happening here. So we're defining, we're consuming these parts, we're creating activities if there are no tasks for how this part is made, where we may have to modify tasks or activities, I'll call them activities, where we have a situation where the product has changed enough that the task and activities have to be changed. So this consumption is very important. We have a process tree on the left. We have components that are essentially needed to be assembled in this operation, let's say, which is a collection of activities, and we need to make sure that we're not violating precedent. So we're going to do some visual validation. We have the 3D CAD model that we bring in. We know what parts are consumed by the tasks in the station, and we're able to visually, virtually build this product at this stage. We can also visually, virtually map consumption. In other words, we can drag a part from the 3D model into the process tree task where it needs to be consumed. Or we can move tasks around in the tree if they're not done in the proper precedence order, if they're violating precedence. So there's a lot of co-authoring. We're modifying the process itself and the process's consumption so that the new version of the product is essentially reconciled with the process. We don't have parts that are being consumed by the process that are not in the current MBOM, right? We don't want that to happen. We want to make sure that only the parts that are in the current MBOM are consumed by the current process. They're consumed in tasks that are performed at the right place, at the right time, relative to each other, and in stations that have the proper resources. So this is a very important stage in this process. And this is where we're doing this, what we call activity and time authoring, this stage 2. And of course, that also means that when we're defining these tasks, we're not just concerned with consumption, we're also concerned with, are they safe to be performed? Are they ergonomically safe? How long do they take? So the time study, are they efficient? Are they lean? So this gets back to our definition of the process, this terminology, routing all those tasks on the line, operation, the collection of tasks we assign to people, but eventually those people get mapped to a station, and activity, which are the tasks themselves. So Once again, defining precedence will automatically start from a serial sequence of activities ordered from the routing. That's why I say that precedence is going to bring it in initially by looking at the BOM structure, the M-BOM structure, and then we're going to basically alter it to ensure that we have as much parallel precedence as we can, because we don't want a sequence that becomes very limiting when you're doing line balancing. We want to know what tasks could be done parallel to other tasks. We don't want to be given, well, just do it this way and not consider the other ways the product could be manufactured. So adding parallelism between activities where appropriate provides opportunities for much more efficient line balances, and integrated access to the virtual 3D build model assists in defining this precedence, as you can see. Of course, here's just an example of looking at our value-added, non-value work content, our time studies. We've already looked at consumption. So this is just that whole process authoring segment. Now, once we've authored the process, once we have tasks and we know their precedence and we know the tools that are required, okay, now we can start looking at where do we want to perform the tasks and which operators should get which tasks in which locations. So this is the line balancing phase. And so once again, we do want to look at how long the tasks take. This is a Yamazumi chart. You can see at the bottom here, the 3 bars that are grouped together represents 3 different models of a product being made in a station. The gray bar at the very bottom reflects these stations, or as actually in this case, these are operations, because we could have more than one operator in a station. We might have multiple gray bars working parallel in the same station. But regardless, we need to be able to map these activities, which are represented by these tiles of different colors, red, yellow, green, in this case, reflecting value, non-value, and non-value necessary. They could also be color-coded by work zone. They could be color-coded by right side of the assembly line, left side of the assembly line, inside the vehicle, underneath the vehicle, however we wish to do that. But we still are able to relate to the 3D model because each of those tiles knows what parts it consumes. We have the 3D model handy as we move these tiles around in the facility to the different stations. We can visually validate the assembly sequence and make sure that it's not violating precedence. So obviously, whether we're dealing with a new or existing line, we may be adding or removing stations. We're going to import build schedules, or we're going to estimate percentages of model X versus model Y in order to evaluate how these different cycle times, okay, associated with operations or with people in stations are going to affect the overall line's production rate or its takt pace. Of course, once again, as we're moving these activities around to different operations, different operators in different stations, we're also moving their parts and we're also moving their tooling. Once again, we're not typing anything in. We don't have a separate Excel spreadsheet. We have a data model. We have a digital thread of the process consuming the product that's being moved at the same time. So this just reflects another view of how this assignment will eventually look. And this is just a high-level view, once again, showing where we're at, where we had the process authoring. We've done this before and after line balancing assignment, and then we essentially aggregate and publish out what that assignment ended up being. So station 1 has activity 1, 2, and 3 in it. Station 2 has activity 4 and 5 in it. I can take all the tasks in station 2, all the activities, and their parts that they're consuming and their tools are consuming, and publish them out into tooling reports and logistics reports, what parts need to be there, so we can work on our line side presentation. We know the roll-ups of ergonomics, so we know all the collective ergonomic issues that person will be exposed to. We know that if this collection of tasks is safe to perform. We have all the work instructions associated with each of those tasks that get compiled into an overall work instruction document for that operator at that station, which reflects essentially all the things that that operator could be required to do, and all the parts that operator is going to have to work with, and all the tools that operator is going to need. Of course, in the MES system, based on a specific customer order, we're going to filter out some of those activities that are not applicable to a particular unit, so we can generate to that operator dynamically, real time, what that operator needs to do, what tools and parts they need to put on and work with for that specific unit they're making. Now, this is where we get to that. Once we've done our assignment, we validated that process assembly. It's very important. We don't have to do these 1 week, 2 week long ramp up periods on the line for a new product introduction. Because with the digital twins, with the digital thread of information, with this manufacturing process knowledge base, I can digitally validate and verify that this production system is capable of producing these versions of these M-bombs with this defined bill of process before we start production. So work instructions, this is this validation. Can we commit to this? What are the parameters of the scenario? Is this, the production rate we're after? Are these truly the model mixes we're expecting to see? If they aren't, and they fluctuate too much, if instead of 70% Model X, we're only 30% Model X, what does that mean? Can we produce this product? Once we commit to a plan, we are going to publish this as a scenario, and we can publish this scenario to the execution system. Once again, in the process of consuming the CAD model and defining the process plan, we're also able to take snapshots and generate our shop floor work instruction document images. We can then annotate it with our textual descriptions, and essentially we're authoring the process and documenting the process at the same time. Very powerful, very accurate, very efficient to perform. We can also, while we're doing that, add in things that we want the operator to know. Those might be control plan items from a quality perspective. Those might be data collection points from a history or genealogy, where we want to make sure the operator is scanning the transmission or the engine or the axle, so we know exactly which one went on the product, or whether the operator is required to enter data about the quality of the item. So the work instruction document isn't just a PDF file. It's an actual interactive document for the worker, or an interactive document for the tool. For example, in the DC torque tool, where the process engineer entered 50 foot-pounds, the work instruction document can communicate the 50 foot-pound requirement as a tool set to the DC torque tool in that workstation. That becomes part of the digital thread of this model. The digital twin, is, if you will, of the production line, represents the equipment needed, both automated and manual, in that line. Once we get to the final stage, we're going to jump between 4 and 5 here a little bit, but what we're really doing is we're publishing. We're not just creating, once again, a work instruction document, but we are electronically communicating bidirectionally with the worker. They can make notes in the system as part of problems that they see happening to the quality of the product or the tooling or a problem in their station. And those notes come back to the process engineer who authored those work instructions electronically, creating a digital thread. Once again, we're also tracking what was put on. We're tracking which operator put the part on for which customer order at what time. And we're showing this in a dashboard environment, like an and-on board, in many different ways, also part of the system. The logistics is just as important as the MES assembly instruction part documentation process. In logistics, we need to know that this part, this product that we're going to make in the station needs these parts, and they're delivered in a kit. So the system, Proplanner in this case, is able to generate the part kit appropriate for the set of stations that part kit will be used in. Maybe one station, or maybe travel with the product 2 or 3 stations down the line. We need to know what goes in there. Once again, digital thread, the data is linked. So if I change where the task is performed, I have changed where the part is needed. And that may mean I'm also automatically changing what part kit it shows up in. And then we're tracking what happened. So in this publishing phase, as I mentioned, step 4 was a publishing, step 5 is the execution. We have the work instructions, the MES part, and we have the logistics part, as we see by both 4A and 4B. The final stage, this is the actual execution. That's where these instructions, these actual part kit lists are being, and line side presentation reports are being implemented. And so back here now we're in step 5, where we're actually communicating with the workers in live from a published work instruction, a published PFEP, a published MBOM and routing for a particular scenario that we are currently working on. Of course, we authored in step 3 many scenarios. Remember the bill of process scenarios, maybe for a 14-person line, a 16-person line, 18-person line. So I can always go back and republish step 3, changing the configuration of the stations, the tooling and the parts, republishing 4A and 4B, the work instructions and the logistics plans, so they can then be re-executed at an effectivity date, a date in the plant where that new scenario's published version is actually live. Step 5. So you can see how that relationship works. So we get to logistics, and we're looking at this step 5 gate from an execution perspective. It's important to note that there are, parts, locations, and equipment from logistics to be used. It's really a 3-stage process, and this gets into the life cycle of logistics, and that's why I wanted to just jump into this one. There's actually a life cycle in work instructions, which I've hinted at a little bit. But even though we're in a phase, there's a systematic approach where that phase has to be performed to be done efficiently and concurrently to allow for concurrent endurance. So we talked about publishing to the floor. We talked about the shop floor visibility to the worker, the ability of the worker to make notes and comments as they're producing the product, but we're also talking about the logistics tracking, right? We're talking about a dashboard showing us what part kit is being generated based on what published PFEP database. In other words, what plan for every part was published based on that published scenario, production scenario, that published bill of process to the line that said these tasks are going to be done by these people in these stations. Here is the current part kits and parts, and this is the status that they're in at the execution level in stage 5. So obviously, for this logistics data to be authored, we have this incoming data with regards to these parts and their locations, which we'll get to in a moment. This is an example of what it may look like. And in fact, in this particular case, we may be even looking at containerization at the first stage of PFEP. If it's a new product, I may not even have an in-plant container for it. And I'm looking at what my appropriate containerization should be. Stage 2, I'm looking a lot more about how I'm going to move it around based on, is it going to be in a plant-based supermarket? Is it going to be stored only in the warehouse and retrieved? Will it have multiple consumption locations on the plant floor? So we're basically defining all the different places where this part is stored and consumed. And then eventually we're going to define how it's actually delivered. What equipment is required for moving this? Is it done by tugger? These parts, are they, and these kits and these kanbans, are they moved by fork trucks? Is it delivered automatically by a conveyor? And examples of what that looks like also through tools that Proplanner offers to assist with this final PFEP stage in the plant. So I want to go back to where I started, publishing gates. We talked about the first gate when we received the ECO and the EBOM and the CAD model. We talked about the second gate when I've defined my tasks. I've got my MBOM. I've defined my bill of process. To the third gate where I'm mapping the bill of process and the part and tooling and labor requirements to actual stations where I'm assigning equipment, I'm assigning parts, I'm assigning people, to the validation and publishing phase where I'm actually generating shop floor work instructions based on a production scenario. I'm generating logistics plans based on a scenario. I'm sending out MBOMs and routings to ERP based on a scenario, which will have an effectivity date range from one date to another. So digital T is the twins, the digital twins of the products, one for every customer order, if you wish, one for every product configuration you plan to build, that are constructed via this digital thread, this bill of process, this bill of materials that manifests itself into a data model of not just the product's components, but the product's process where it comes to life. I wanted to mention just a few more data relationships that are important to think of And here's more of a data flow diagram look at it. We have processes, we have products, and we have plants. So obviously line balancing really fits in the center of this because I have these product models in my virtual build. I have these tasks that I need to balance that are consuming those product models. And based on different balances, I have different views of the product at different stages in production, right? For every one of those line balances, I have different buffer situations based on an actual production schedule. If I do batch production of similar things at once, if I do full mixed model production, and for each one of those on the PFEP side, I have a logistics plan, once again, based on where I've assigned the work. So, and of course, the workplace is different. The tooling's different. The task allowed to the workers is different. So there's on the layout perspective, I have an operator walk path analysis. That's a workplace planner. I have a product and component flow analysis. And through the factory, that's a flow planner analysis. I may have a simulation of the workplace model, a buffer analysis of the assembly line. You can see how product, process, and plant relate. Plant, product, human. Once again, the line balance being communicated with the process and the ergonomics assessment, because of course, as I group 3 or 4 activities together, I may find a situation where those activities individually are safe, but collectively don't work. Even if the balance is great, even if the precedence is okay, we could be rejected due to an ergonomics problem. Obviously, once again, based on that assignment of work, I can then model the entire ergonomic forces in Workplace Planner, the walk path in Workplace Planner, and make sure that the workplace model and the human model makes sense. Product, process, machine. So now what I'm looking at is what's tooling required? What tasks am I asking the machine to do? Is it within the capability of the resources that are being required? And I might link in CAM tools. And in fact, in some cases, we're actually taking basically NC code files or tool set ID files for machine tools as part of the process task description and publishing them to the resources. But of course, those resources have to be in those stations that those tasks are now currently assigned to. So we can publish those out to the equipment to do validation and verification. Now, we don't do that directly. That CAM is not an area that we get into. We don't do any robotic offline programming or anything, but we can communicate, transfer the data required by those systems. So we look at validating the product, process, plan, and resource, we call 3PR, with logistics, the plus L. We can reconcile the EBOM to the MBOM. You've seen us do that. We can reconcile the MBOM to the routing through process consumption and activities, making sure that the routing is only consuming parts in the active MBOM. And we can even do so on a model by model basis. We can generate customer orders through this system and then verify that indeed every custom order you want to build is capable of being built by the bill of process that we've authored that's consuming the bill of materials. We can reconcile the writing activities to the assembly line. We can verify that the tooling and the people are there in those stations capable of building those products and that within the takt time defined. So what does it mean to be able to validate this? What does it mean to be able to take your product, process, plant, resource, and logistics and actually fit it together electronically before you produce your products? Well, it means that parts and tools are in the correct station right off the bat. Supply systems can keep them replenished because the supermarkets have been validated. We validated PFEP. We reconciled PFEP, the plan for every part, to the assembly line. And the assembly line components and tools was validated with the line balancing, right? To make sure that it can produce what we need to produce. Electronic work instructions allow for interactive engineering build during the first week. We have work instructions from the CAD models. Workloads are correctly balanced between operation stations. Because once again, when we did our reconciliation, we did it within a line balancing environment that showed the cycle time of each station for every model produced, for every customer order that we chose to validate or evaluate. But those can all be produced within the takt time. In other words, no cycle time of those stations exceed the takt time. New product launches can happen relatively quickly. We've seen customers take 4-week product launch cycles and get them done in a week or less, which can save a tremendous amount of time in terms of inefficient or offline production capacity. Now, of course, this digital thread, this digital manufacturing process that we're outlining, these digital twin data models of customer orders that we're creating, is very different for the organization. This puts the organization, the engineers, in a lot more computer-driven, model-based, day-to-day workflow than maybe they were doing before. Less running around chasing, dealing with last-minute issues and problems, and more upfront planning. In other words, the work day of the engineer will be different. As we call it, someone will move your cheese, okay? You will spend more time engineering the process in the plant, but it will be more productive time, not just updating a new Excel spreadsheet and moving the lines around a bar. You'll actually be working in a workflow authoring system designed specifically for assembly process planning in a digital manufacturing context. Your team will need to collaborate. In other words, the process tasks that are being authored for time studies are the same for ergonomics, are the same for work instructions, are the same for line balancing, are the same that's sent to ERP, are the same part consumption lists used for your logistics team. Everyone is driving off the same digital model. Today, in your organization, is a pretty good chance there's an Excel spreadsheet managed, developed, and updated by each of your groups: line balancing, time studies, work instructions, ergonomics assessment, all independently. Now you have to share, and the gated process will allow that to work in a concurrent engineering environment, but it is going to change how you do your work. This process works. It's implemented. This isn't a PowerPoint presentation only. This is an overview of a system that actually delivers value. And that's really what Proplanner is about. It's a group of industrial engineers who've worked for over 30 years on refining the process of bringing complex assembled products to market quickly, pre-engineered applications around proven workflows, providing solutions for your team today. Accurately integrate electronic part and process data flows, reducing errors and getting you into production faster. And open XML data sets, Microsoft SQL Server data tables, industry standard architectures with accessible data formats allow you to get your information into our application and to utilize the information in our application externally to drive or communicate with other systems in your organization without heavy, expensive customization or proprietary interfaces, all for a low annual monthly fee on subscription. No big upfront multi-million-dollar contracts. This is just about providing users with the tools that they need, a whole portfolio of tools, no more individual modules, the entire suite per monthly fee per user. They use whatever tools they need whenever they need them. That's what collaboration is all about. Hopefully you found this overview of Proplanner's Digital T to be helpful. And as always, if you have any questions, please get a hold of us. Thanks.